Hey everyone, Mr. Fritz here. We are going to talk about graphing logs. We have simplified logs, we have solved logarithmic equations, we solved exponential equations. Now let's actually put these things to a grid and graph them. Let's first think about some inverse function stuff. If we think about inverse functions, we're going to have an easier time graphing these things because they're kind of tough to wrap our mind around. Three things we need to recall. Number one, inverse functions can be found graphically by switching x and y values. So if I have some point AB on some line f of x, then that means that the point BA lies on f inverse of x. So we should know this. Secondly, if I have the function y equals f of x, that is a reflection of the line over the curve y equals f inverse of x over the line y equals x. So remember that y equals x kind of makes like a mirror, and the function and its inverse kind of reflect over that mirror. And then the third thing is the domain and range switch between inverses. So that should make some sense. Since the x's and the y's switch, so too do the domains and ranges switch. So everything with x goes to y, everything with y now goes to x, and that's an inverse. We are kind of inverting the whole order of my coordinates and the direction of my mapping. All right, so keep those things in mind as we talk about graphing logs. And I think it's helpful to think of them as inverse exponentials, since that's kind of what a log is by definition. So I want to take a look at the function f of x equals a to the x. So this is just some exponential function. And we know that with these exponentials, a is going to be greater than 0, and it's not going to equal 1. And if I keep those two constraints, I can have two things happen. A can be between 0 and 1, or it can be greater than 1. So let's see what happens when I have that a between 0 and 1. Now, if you remember what that means for exponentials, this could be like a half, or it could be a third, and basically what you're doing is you're multiplying 1/2 by itself over and over and over, or 1/3 by itself over and over and over, and you end up getting a smaller and smaller and smaller number. So this is an exponential decay. And it looks something like this, give or take. And we know a couple things about this. I'm going to note this as f of x. We know that the y-intercept is always going to be, as long as it's in this form, it's going to be 0, 1. That's because anything to the 0 power is 1. I also know that this point here, 1 unit out, is going to be, this would be -1. This coordinate is going to be -1, 1 over a. And I know that this coordinate, 1 unit out here, is going to be 1, a. And I can continue this pattern, so on and so forth. So that is my exponential function. Now, if I remember that switching all these coordinates, x's and y's, makes for a logarithmic graph, and I have to kind of visualize reflecting over this mirror, the logarithmic graph looks a little bit different. We also have the domain and range switches. Right now in this exponential function, I have a horizontal asymptote of y equals 0. That means, and let me just kind of jot that in here. Here's my horizontal asymptote. That means that my logarithmic function will have a vertical asymptote of x equals 0. And what's going to happen is that the point 0, 1 now becomes 1, 0. The point 1, a becomes a, 1. The point -1, 1 over a, that switches and becomes 1 over a, 1. And what we end up getting is some kind of a picture that looks sort of like this. So give or take. And you can kind of see the reflection going on here in this line of y equals x. And I didn't draw this perfectly, but what we're seeing is both of these are decreasing as we move forward, and that's fine. And all of the x and y values have switched. So this is my f inverse of x. This is my logarithmic graph. All right, so that could be if a is between 0 and 1. Let's think about what happens if a is greater than 1. And I'll kind of speed through this one a little bit faster this time. If a is greater than 1, I have exponential growth. So this is going to look something like this. And once again, the y-intercept is all those general properties about the y-intercept and all that stuff. This is all still the same. But now when I graph my logarithmic function, it's going to reflect, and once again I'm going to have, I'm just going from a horizontal asymptote of y equals 0 in the original function to a vertical asymptote of x equals 0, and I'm going to get a picture that actually looks something like this. So this is my f inverse of x, my log graph, and this would be f of x. And I can actually go take my f inverse of x a little bit further, and I can actually state what the inverse is of this. This would be log base a of x. And it should look something like this. You know, once again, it's not perfect, but we can see that there's a little bit of a reflection going on. And really what's key to keep in mind here is when you are graphing exponentials, you're inputting power or exponents, and the output is the full power. When we switch to our logarithm, we are switching the x's and y's. So rather than our x's being the numbers that we're putting in, I like to think of it as we are getting out the x's from the y exponents. And I'll show you what I mean in our first example. First, before we do our first example, let's talk a little bit about domain, range, and asymptotes. So what we saw in those previous graphs, we can kind of gather what the domain and range is. Let's talk about these one at a time. The domain of my exponential is going to be all real numbers from negative infinity to infinity. Or you might also see this notation, x is an element of the real numbers. And so the range we also saw is that there's a horizontal asymptote that never touches it. So we have a 0 to infinity for our y values. And for our asymptote, we said that y is equal to 0. So because the domain and range switch, all the x's become y's, all the y's become x's, what's going to happen is I'm actually going to move the domain of the original function to the range of the inverse function, and do the same thing with the range of the original function into the domain of the inverse. So we're just going to swap all these guys. So this is 0 to infinity, and then this is negative infinity to infinity for the range, or in this case we could say y is an element of the real number set. And then now my asymptote is no longer y equals 0, but it is the vertical asymptote x equals 0. So just to kind of keep that in mind. These are all when I have these very basic graphs, but if we shift things over or stretch and compress things, that'll affect these numbers too. So let's graph one of these guys together. We want to graph just the function f of x equals log base 2 of x. And now if I think in my exponential frame of mind, and I were thinking the exponential y equals 2 to the x, normally when you would graph these, you would create a table of values, and you could put in all kinds of different values for x, negative 1, 0, 1, 2, 3. And remember that you're kind of coming up with these x values just as a successive integers, and you're using these as exponents. And then what you do is you'd kind of evaluate them, plug them in, and you'd get 1/2, you'd get 1, 2, then 4, then 8. And what comes out for my y values, the output of my exponentials, are the powers. So these are all powers of 2. When you're graphing a logarithmic function, you're switching your x's and your y's. So let's compare this with y equals log base 2 of x. Essentially what I'm doing here is my x values and my y values are the exact opposites of what I have for my exponential function. So now I have 1/2, 1, 2, 4, and 8, and negative 1, 0, 1, 2, and 3. And in this case, my powers are my x values, and my exponents are the y values. And that should make sense, since the thing that comes out of a logarithm is an exponent, and the thing that goes into a logarithm, well, I mean, the numbers that you'd prefer to go into a logarithm are ones that work out nicely with the base. So once we kind of have this in mind, we're ready to graph this thing. So let's kind of put these coordinates down. I've got 1/2, negative 1. I've got 1, 0. I've got 2, 1, 4, 2, and 8, 3. So it looks something like this. And we have this, let's actually label our x-intercept. That's a good practice. So this is 1, 0. And I've got that x equals 0 vertical asymptote. And I would kind of sketch that in there too. All right, those are all the important pieces of this graph. It's done. We could always check this on the graphing calculator as well. We can go to the table and look at that. And we can kind of look at how to do that on the calculator later on. But for this basic example, we kind of just want to have a sense of where these values come from. So why don't you try this example on your own? Same type of function. It just has a different base. Pause the video and go through this whole example and make yourself a nice graph, and we'll see how it goes. All right, and this is my function here. I guess I did forget to label my vertical asymptote. This is x equals 0, and pretty similar to the last one, just with some different numbers. Hopefully it went all right.